Okay, let's dive into a paradox that honestly shouldn't make any sense. We're going to explore how a 2,000-year-old material can be so much stronger and more durable than anything we can make today. We're about to unlock the secrets of Roman concrete, a substance that just seems to laugh at time.
Just look at this. On the left, you've got a modern overpass, built with all our advanced engineering, and we're lucky if it lasts 50 years. But on the right, that's the Pantheon in Rome. Its concrete dome has been standing for over 1,900 years, and it doesn't even have any steel reinforcement. The difference here is just staggering, and it raises a huge question.
So, how on earth did they do it? This isn't just a cool history lesson, it's a genuine scientific mystery, and figuring it out has massive implications for our future. To solve it, though, we first have to look in the mirror and understand the fatal flaw in our own approach.
All right, let's start with the material we build our entire world on and expose its hidden and very expensive weakness.
Back in the 20th century, we thought we'd hit the jackpot with Portland cement. You mix it with steel reinforcement and suddenly you can build bigger, higher, and faster than ever before. It really felt like a giant leap forward for humanity. But that leap came with a hidden cost.
You see, the whole idea behind modern concrete is to create what engineers call a closed system. The goal is to make an impenetrable fortress, a perfectly sealed, chemically inert box that's designed to protect the steel rebar inside from all the nasty stuff outside, like water and salt.
But here's the problem with fortresses. In the real world, they always get breached. It starts with tiny little micro cracks from everyday stress. Then, water and other corrosive stuff inevitably seep inside. And that's when they find the steel, which, of course, begins to rust. Now here's the killer blow. Rust actually takes up more space than the original steel. This expansion acts like a powerful wedge, literally blowing the concrete apart from the inside out.
And the price tag for this slow-motion failure? It's just astronomical. The annual global cost of corrosion is estimated to be over $2.5 trillion. A huge chunk of that is just us trying to repair or replace our crumbling concrete infrastructure. It's a completely unsustainable cycle.
So, with that modern mess in mind, let's rewind the clock and head back to the ancient world, where a totally different story was being written in stone.
Roman marvels like the Pantheon didn't have any steel rebar. They are completely unreinforced, and yet they've survived everything you can imagine: earthquakes, wars, centuries of neglect. And what's even crazier are their harbor structures. These things have been sitting in corrosive seawater for 2,000 years, and in some cases, they've actually gotten stronger.
And, this isn't just us looking back with modern science. The Romans themselves knew they were onto something incredible. The writer Pliny the Elder was watching this happen back in the 1st century. He wrote that the concrete becomes a single stone mass, impregnable to the waves and every day stronger. He saw it with his own eyes.
This kind of durability was no accident. It was brilliant chemistry. So let's break down the ancient recipe and uncover the science that made it all possible.
Okay, here is the absolute game-changing difference in philosophy. Roman concrete was an open system. Instead of trying to wall itself off from the environment, it was engineered to interact with it. It literally uses the elements as a tool for its own survival.
And this is the part that will absolutely blow your mind. The very thing that is kryptonite to our modern concrete, water, is the lifeblood of the Roman stuff. Water is the catalyst. It's the fuel that allows Roman concrete to heal its own wounds and actually grow stronger as it ages.
So how in the world does this self-healing work? Well, it all comes down to the recipe. Turns out, the Romans mixed their concrete at incredibly high temperatures. This created these unique, brittle pockets of lime. So when a tiny crack forms and water gets in, it dissolves these pockets. That releases a rush of calcium-rich goo that recrystallizes and seals the crack shut. It's like a built-in repair crew. And for marine structures, they added volcanic ash, which reacts with seawater to grow tough interlocking crystals, making the concrete even stronger. Incredible!
So let's just put this side by side, because the difference is night and day. Modern concrete is a closed system that fights a losing battle against water. Roman concrete is an open, reactive system that uses water to its advantage. One relies on steel that is doomed to fail, the other needs no reinforcement at all. It is a totally different way of thinking about building.
So this is more than just a fascinating history lesson, right? What do we do with this ancient wisdom? Well, this is all about building a smarter and way more sustainable future. What we're learning from the Romans isn't just about admiring old ruins. It's a literal roadmap. It's a blueprint for a whole new generation of smart,
resilient materials.
I mean, just imagine what we could do with this. We could develop new, low-carbon cements that mimic these ancient reactions. We could create a whole new class of living concrete that actively heals itself, making our bridges and buildings last for centuries. This wouldn't just save us trillions of dollars in repairs, it would massively shrink the giant carbon footprint of the construction industry, which would be a huge win for the climate. We could finally start building for our great-great-grandchildren, not just for the next few decades.
And that really leaves us with one last big thought. Roman concrete proves that sometimes the most groundbreaking innovations aren't about inventing something brand new, but about rediscovering the brilliant wisdom we've lost along the way. It just makes you wonder, what other ancient solutions are hiding in plain sight, just waiting for us to find them?
So how is this possible? How can their stuff last for ages while ours can start falling apart so quickly? Well, the answer isn't some single magic ingredient. It's more like a scientific detective story. And what it reveals is this incredibly ingenious dynamic system. We're talking about a material that wasn't just built to fight the elements, but to actually work with them. And get this, it gets stronger over time.
All right, Section 1, Rome's Enduring Concrete Mystery. So to get to the bottom of this, we're going to look at 3 key pieces of the puzzle that Roman builders absolutely perfected. First, a very special kind of volcanic ash. Second, a totally revolutionary lime mixture. And third, a very surprising partner in crime, seawater.
Okay, let's get into it. Part 2, the key, volcanic ash. So our first major clue, and this really is the cornerstone of Roman concrete, it all comes down to a super unique material. The Romans got it from the Bay of Naples, which, is a hotbed of volcanic activity. Yeah, this stuff was not your average beach sand. It was totally different, geologically speaking. They called it pulvis putillinus, basically the dust of Puteoli. It came from these massive volcanic eruptions where the magma cooled down so fast it didn't have time to form crystals. Instead, it became this glassy, super reactive material. And that was the secret sauce that let them create a concrete that could actually harden underwater. So check this out, because this is where it gets really interesting. This slide breaks down the fundamental difference. You see, in modern concrete, we use sand as just a filler. It's inert, it doesn't really do anything, it just sits there. But the Roman volcanic ash? Oh man, that was a whole different story. It was like an active chemical engine, just packed with these reactive minerals that were ready to go, ready to dissolve and form brand new, super strong mineral bonds. And listen, this wasn't some happy accident they stumbled upon. They knew exactly how special this stuff was. You have the famous Roman engineer Vitruvius writing about this exact ash, pointing out its incredible ability to harden in the sea. The empire thought it was so valuable, so crucial, that they set up this massive logistical operation. We're talking shipping thousands upon thousands of tons of it all across the Mediterranean to build their harbors and monuments. It was a huge deal. All right, Section 3, a revolutionary hot mix. So, okay, they had the perfect ash. But how did they glue it all together? Well, the answer is lime. But, and this is the crazy part, it turns out they used it in a way that we've only just figured out. A method that was fast, furious, and literally hot. You see, for the longest time, scientists just assumed the Romans did things the modern way. The theory was they used a slow, careful process. They'd mix quicklime with water first, make this nice, stable putty, and then add it to the ash. It made sense because it's kind of how we do things now, and it seemed to fit with what the old text said. But there was this one nagging problem with that theory. These little white chunks you see everywhere in Roman concrete, they're called lime clasts. And for years, everybody just wrote them off. They thought, oh, that's just sloppy mixing, bad quality control. But then, a huge study in 2023 flipped everything on its head. It turns out these weren't mistakes at all. They were the smoking gun. And what that smoking gun pointed to was a technique called hot mixing. So instead of carefully making that putty first, the Romans were just dumping highly reactive quicklime directly into the wet volcanic ash. Now, this sets off a powerful chemical reaction. It's exothermic, which just means it gives off a ton of heat. The whole batch basically turns into a high-temperature chemical reactor. So why do this? Why make it so hot? Well, there were 2 massive advantages to this. This was basically ancient high-tech. First, all that heat acted like a chemical accelerator. It made the concrete cure way, way faster, which meant they could build things much more quickly. And second, the intense heat created these unique mineral bonds that you just don't get at normal temperatures. And that is a huge part of what gave the concrete its incredible strength and durability. Okay, on to the final piece of our puzzle. Section 4, seawater, the secret partner. And honestly, this part is a total game changer, especially when you're talking about structures built in the sea, like harbors and piers. Now, think about this. Today, salt water is like kryptonite for concrete. We do everything we can to keep it away because it gets in and rusts the steel rebar, and then the whole thing just falls apart. But Roman concrete didn't have any steel rebar, and that meant their engineers could do something that to us sounds completely crazy. They actually designed their structures to use the seawater. So this is the truly mind-blowing part, this self-healing cycle. Their concrete was actually designed to let a little water in. So seawater would seep into tiny cracks, right? And when it did, it would dissolve some of that still reactive volcanic ash and those lime clasts we talked about. This would kick off a new reaction, growing new interlocking crystals that would literally fill in the cracks. The structure was constantly, actively repairing itself. It's like it was growing geological scar tissue that made it even stronger as time went on. Okay, let's wrap this up. Section 5, Lessons from an Ancient Recipe. So when you put all these pieces together, the special reactive ash, the crazy hot mixing, and this incredible self-healing power of seawater, you start to see a philosophy of building that is just completely different from how we think today. And this chart really just says it all, doesn't it? Our modern concrete is built to be static. It's designed to be a brute force barrier that just resists the environment until, it finally cracks and fails. Roman concrete was the complete opposite. It was designed to be dynamic. It was meant to interact with its environment, to evolve, and to actually heal itself.
So it all seems to boil down to the glue that holds everything together, the binder. Modern cement uses what's called calcium silicate hydrate, or CSH. But the Romans, by using volcanic ash, added a crucial extra ingredient, aluminum. This created calcium aluminum silicate hydrate, CaSH. And that A for aluminum? It created a chemical structure that was way more resilient. But believe me, that's just the tip of the iceberg. Our first huge clue comes from these incredible marine structures, these harbors that have stared down the sea for millennia. And this is where the story gets really wild.
So scientists were analyzing this harbor concrete, and they found something that shouldn't be there, aluminum tobermarite. Now you're probably thinking, what in the world is that? Well, it's a super rare mineral. You normally only find it in extremely hot places, like inside a volcano, at temperatures way over 150 degrees Celsius. So what was it doing growing inside concrete that cured in cool seawater? It made no sense.
And to say this was a shock is a massive understatement. The entire scientific community was floored. It just shouldn't have been there. It was like finding a palm tree growing at the North Pole. It broke all the rules, and it meant there was a huge piece of the puzzle we were all missing.
Turns out that missing piece was what some call an exothermic kickstart. See, the Romans used quicklime, which has this really intense reaction with water. The reaction created a massive burst of heat right inside the concrete, pushing the temperature up to this range, 85 to 97 degrees Celsius. It wasn't volcano hot, but it was just hot enough to give the concrete the energy it needed to start growing those rare, super strong tobermite crystals.
And here's the absolute genius of it. Over the centuries, as seawater seeped into the concrete, it didn't damage it, it fed those crystals. They kept growing, interlocking with each other, creating this incredible internal reinforcement at a tiny scale. It's literally like microscopic rebar, making the whole thing tougher and more resistant to cracks. The very thing that should have destroyed it was actually making it stronger. Okay, that's the seawater secret. But what about buildings on dry land, like the Pantheon? They didn't have seawater to work with. Well, they had a totally different trick up their sleeve. And honestly, this one might be even cooler.
For years, if you looked at Roman concrete, you'd see these little white chunks scattered in it. And for the longest time, everyone just assumed it was, sloppy work, a flaw from bad mixing. But recent studies revealed we had it all wrong. They weren't a mistake. They were put there on purpose. They're not a bug, they're a feature.
The best way to think of them is like tiny little chemical batteries, or maybe like first aid kits embedded all through the structure. They just sit there, dormant, scattered throughout the concrete, waiting for the one specific trigger that will activate them.
So here's how it works. A small crack starts to form. It's inevitable. That crack eventually runs into one of these brittle little lime clasts. Then it rains. Water seeps into the crack and dissolves that little white chunk, creating a calcium-rich goo. This solution then flows down into the crack, and it recrystallizes, sealing the gap completely shut. It's a simple, brilliant, and fully automatic self-repair system.
And this is incredibly effective. In lab tests recreating this, the Roman-style concrete healed cracks 0.5 millimeter wide. That's a crack you can see in just 2 weeks. This is a huge reason why the Pantheon's dome is still standing after nearly 2,000 years of tremors and weather. It just keeps healing itself.
So after uncovering all this incredible ancient wisdom, what does it mean for us? What do we do with these lessons from the past?
So let's just recap the 2 mind-blowing technologies we've unpacked here. For their marine structures, they designed a concrete that uses its own harsh environment to get stronger. And for their architecture, they invented a smart material with its own built-in automated healing system. 2 totally different challenges, 2 absolutely brilliant solutions.
Okay, so the secret really starts with their whole approach to building. The Romans called their concrete opus caementicium. But the real key wasn't just what was in it, it was all about how they put it together. And this right here is the heart of it. Modern construction, on the right, it's all about this fluid, liquidy slurry that you just pour into forms. Easy. The Romans, though, totally different game. They worked with this much stiffer, kind of dry, zero-slump material. You couldn't pour it. You had to build with it, piece by piece, layer by layer. So here's how they did it. It was this incredible 4-step process. First, the formwork. They'd build these permanent walls that acted as the mold. Then, the aggregate. Workers would literally hand place these big, fist-sized chunks of stone inside. Next up, the mortar. They'd spread their special mix of lime and volcanic ash all over the stones. And then, and this is the most important part, the tamping. They would just pound that stiff mortar down with heavy tools, forcing it into every single little crack and void. Now, this wasn't just brute force, it was a brilliant technique. All that pounding made the whole mix incredibly dense and got rid of any air pockets. And get this, modern engineers actually have a name for a similar process, roller compacted concrete, or RCC. And we use it today to build massive things like dams, precisely because it's so strong. But here's the catch. It takes a ton of time and labor. Our modern pourable concrete is just way faster and cheaper, and that's really why our priorities have shifted. So how did this hands-on method let the Romans build something that honestly seems impossible even now? For that, we've got to look at the ultimate case study, the Pantheon in Rome. Just let that number sink in for a second. A dome spanning over 43 meters. That's wider than the dome of the U.S. Capitol building. And it was built almost 2,000 years ago, with no steel rebar holding it all together. To this day, it is still the largest unreinforced concrete dome in the entire world. You see, the biggest enemy of a giant dome is its own weight. Engineers call it the dead load. All that force is pushing down and out, and it's always threatening to crack the whole thing open. So how on earth did the Romans solve this fundamental problem? Their solution was nothing short of genius. The secret? They didn't use just one kind of concrete. They used a bunch of different recipes. They carefully graded the aggregate, the rocky filler, making it lighter and lighter the higher they built. So down at the foundation, they used heavy travertine limestone for a super solid base. But as they built the dome up, they switched to lighter stuff, like broken bits of brick. And then, at the very top, around that famous oculus, they used pumice, a volcanic rock so light it can literally float on water. And this is the payoff, right here. The concrete at the top of the dome was more than 3 times lighter than the stone in the foundation. It's this huge weight reduction at the very peak that relieves all the stress on the structure. And it's the key to why it's still standing today. It's just an incredible piece of engineering. Okay, so the Pantheon shows their mastery on land. But what about in the water? That's a whole different ballgame, right? The Romans built these enormous harbors and breakwaters right in the open sea. And that took a totally new set of tricks, which the architect Vitruvius thankfully wrote down for us. For places where the seafloor was nice and solid, they used what's called a caisson. It's just wild. They'd build this massive double-walled wooden box, an arca, sink it to the bottom, and then seal the walls with clay. Then, and here's the crazy part, they would pump all the water out, creating a dry workspace on the ocean floor where they could just build like they were on land. Okay, but what if the seabed was just soft sand? You can't pump that dry. So they switched to let's call it a brute force approach. They would form these enormous blocks of concrete on the shore,
let them cure for more than 2 months until they were rock solid, and then just tip these massive things into the water to create their own stable artificial foundation. Whatever works. But this third method, this is where it feels like pure magic. Thanks to their special volcanic ash, pulvis putillanus, they could create a hydraulic mortar. That means it would actually harden underwater. They'd build the formwork right there in the sea, and then just place the mortar mix into the water-filled mold. And the concrete would set and cure, completely defying the water all around it. This was a technology that just blew the minds of ancient observers. So we've got this amazing material and these genius engineering tricks, but that's still not the whole story. The final crucial ingredient that made any of this possible was the immense organizational power of the Roman Empire itself. It's like you can have the best recipe on the planet, right? But it's pretty useless if you don't have the kitchen and the cooks to make it. To build on this kind of scale, the Romans needed a huge, highly organized system of labor and a supply chain that stretched all the way across the Mediterranean. And their workforce was really layered. At the very top, you have the architects and military engineers designing everything. Then you had your skilled masons, the guys who did the beautiful brick and stone facings. But the real engine of the whole operation was a massive force of unskilled labor, often enslaved people, who did the backbreaking work of mixing, hauling, and most importantly, all that tamping. And that entire labor force had to be supplied. You have to remember, that crucial volcanic ash was being shipped from Puteoli near Naples, all across the empire. This took entire fleets of ships, a state-level commitment to logistics, and making sure the materials were up to snuff. This wasn't a local construction project. This was an imperial enterprise, top to bottom. So in the end, the secret of Roman concrete, well, it wasn't just one thing, was it? It was a combination of superior materials, that hands-on construction process, brilliant engineering, and an entire imperial system to make it all happen. They were building for permanence. It's just a different philosophy from ours today, where things like speed, cost, and the strength we get from steel rebar often come before 1,000-year durability.
You know, you see it everywhere. Bridges, buildings, dams, even the sidewalks you walk on. It all feels so permanent, so solid, right? But what if I told you that the modern version of this stuff has a dirty little secret, a built-in expiration date? What if the very foundation of our world is fundamentally flawed?
So to really get this, let's start with the scale of the problem. Just making cement, which is the key ingredient in concrete, is responsible for a staggering 8% of all global CO2 emissions. I mean, think about that. That's more than the entire airline industry combined. For just one single material, that is a massive environmental price tag. So where does this huge carbon footprint actually come from? Well, it turns out it's a 1-2 punch of pure chemistry and just brute force. Let's break down the hidden costs of our concrete world.
It's a double whammy, really. First, you've got the insane amount of energy needed. The kilns that bake limestone to make cement have to get up to 1,450 degrees Celsius. That's literally hotter than lava. And doing that means burning a ton of fossil fuels. But second, and this is the really wild part, the chemistry itself releases CO2. The process is called calcination, and it literally bakes carbon dioxide right out of the rock. So even if you ran the whole thing on clean energy, you'd still have a massive emissions problem.
Okay, so if our modern method is so dirty, you have to ask, is there a better way? And for that, we're going to look to the past, to the Romans. You know, the guys who built stuff like the Pantheon and aqueducts that are still standing 2,000 years later.
And on the surface, the answer seems completely obvious. Just look at this. The Romans only had to heat their lime to 900 degrees Celsius. That is over 500 degrees cooler than what we do today. That means way less fuel and therefore way lower emissions. Case closed, right? Roman concrete is just greener.
Well, this is where the story takes a really fascinating, kind of counterintuitive turn. Because that simple, easy answer, yeah, it's not the whole story.
Turns out, a recent life cycle assessment, which is basically a super deep analysis of the total environmental impact from start to finish, found something really surprising. Because of some of the quirks in the chemistry, just copying the Roman recipe with our modern machines doesn't automatically mean a smaller carbon footprint right out of the gate. The key thing to realize is this: the magic isn't in how it's made.
So if the secret isn't in how it's made, then we have to look at the other side of the equation, how it lives. And folks, this is where Roman concrete changes the entire game.
The key concept you need to know is called amortized carbon. Think of it like this. It's not about the upfront carbon cost to build something. It's about that cost spread out over its entire useful life. A bridge that costs a certain amount of carbon but lasts 500 years has a way, way lower carbon cost per year than one that you have to replace every 50. Makes sense, right?
And that same study actually calculated the break-even point. For Roman concrete to officially be the greener choice, it would need to last about 41% longer than modern concrete. That's the hurdle. That's the number it has to beat to make up for any similarities in production emissions.
And here is the punchline. It doesn't just clear that hurdle, it absolutely obliterates it. We're talking about historic Roman structures that have outlasted our modern ones by a factor of 20. That's a 2,000% advantage. They didn't just last a few extra decades, they've lasted for millennia.
And this chart just shows it perfectly. When you look at the carbon footprint per year of service, modern concrete's bar is really high because you have to keep rebuilding it. But the Roman concrete bar, it's almost too small to see because that initial carbon cost is divided by thousands of years.
And you know, this isn't just an environmental argument. The short lifespan of modern concrete comes with a staggering economic cost, and it's all rooted in one specific, fatal flaw.
The problem is called spalling. See, modern concrete is great at being squeezed, but it's terrible at being pulled apart. So we add steel bars, rebar, to give it that pulling strength. But that steel, it's also its Achilles heel, because when water gets in and that steel rusts, it expands with incredible force, and it cracks the concrete from the inside out. I guarantee you've seen this on bridges and overpasses.
And this whole problem gets dramatically worse in coastal areas. Seawater is packed with chloride ions, which are basically kryptonite for steel. They speed up the rusting process like crazy, causing critical stuff like bridges, piers, and seawalls to fail, not in centuries, but in just a few decades.
So what's the price tag on this failure? Get this, just for highway bridges in the US, the direct cost of fixing this kind of corrosion damage is over $8 billion every single year. And that's not even counting the indirect costs, like traffic jams and lost productivity, which can be 10 times higher than that. It's astronomical.
So what can this ancient technology really offer us today? Well, by understanding its strengths, we can start to imagine a future that's built not just faster, but a whole lot smarter.
The big takeaway here is that it's all about using the right material for the right job. Modern reinforced concrete, it's perfect for a skyscraper that needs steel's tensile strength. But for things like seawalls or foundations, structures that are always under compression, Roman concrete is just vastly superior. It has no steel to rust. And here's the most amazing part. It's designed to get stronger over time. Thanks to its recipe with volcanic ash, when seawater gets into little cracks, it triggers a chemical reaction that grows new interlocking crystals. These crystals actually fill the void and make the structure stronger. It literally heals itself. How cool is that?
So how did we finally crack the code? Well, as we're about to see, the answer wasn't hidden away in some dusty old text. It was unlocked by some seriously modern technology. It wasn't until just recently, using these incredibly powerful scientific tools, that researchers could finally peer deep inside this ancient material. We're talking about things like advanced X-ray diffraction and high-res chemical mapping, basically looking at the concrete at the nano level to finally see what was really going on. Now, this incredible discovery didn't just end up in a scientific journal. Oh no, it has kicked off what you could call a revolution in how we make things, one that's looking to the past to build a better future. Which brings us to this really cool idea, the geomimetic revolution. So what does that even mean? It means we're moving past just admiring ancient tech. We're actively reverse engineering it. Startups are taking these old-school, nature-inspired ideas and turning them into real-world products that can solve today's biggest problems. And let's meet a couple of the people leading this charge. You've got Admir Mazik, who was one of the researchers on that breakthrough study. He founded DMAT to bring that Roman hot mixing secret to the market. And then there's Tiziana Vanorio at Flego. She's taking inspiration from a different natural wonder, a super tough volcanic rock in Italy, to solve the problem of flexibility. And this isn't just some science experiment. This is happening right now. DMAT's product, D-Lime, which has those self-healing lime clasps, is already a real thing. It's actually been certified in Switzerland for these high-stakes projects, like tunnels and mines, where doing repairs is super difficult and expensive. The ancient past is literally meeting modern infrastructure. Flego's goal is a little different, but it's just as much of a game changer.
They're mimicking how volcanic rock forms this natural mesh of fibers to create a concrete that's actually flexible. Think about it. Buildings in earthquake zones that can bend and sway instead of just cracking and breaking, all without steel rebar that can rust out over time.
Okay, so we've cracked the code, we've seen who's bringing it back. But what does this all mean for the world we're actually building? Well, the potential impact is, and I'm not exaggerating here, massive. Get this, studies are showing that this self-healing tech could extend the lifespan of our infrastructure by up to 50%. 50%! Just stop and think for a second what that means. The savings in money, in materials, in carbon emissions. It's just a staggering number. And the possible uses for this stuff are mind-blowing. We could build seawalls that, just like the Roman originals, actually get stronger in seawater. We could build concrete containers for nuclear waste that use their unique structure to trap radioactive particles. And yes, we could even have roads that automatically fix their own potholes. Seriously. So when you boil it all down, here's why this matters so much. You get buildings and bridges that last way, way longer. You get a much smaller carbon footprint because we're not constantly making new cement for repairs. And you get a huge drop in maintenance costs for our cities and countries. It's a win-win-win. But look, this is about more than just a new material. It's a whole new philosophy. It's a completely different way of thinking about how we build our world. This is a total paradigm shift. We're moving away from this old idea of strength through rigidity, just brute force, and we're moving towards durability through adaptability and cleverness. We're going from using inert materials that just sit there and fall apart to using reactive, almost living materials that can respond to damage and heal themselves. So that leads us to their first huge challenge, scale. The Romans didn't just want to build big. No, they wanted to build on a level nobody had ever even imagined before. And to do that, they had to figure out how to conquer gravity itself. Let's just take the Colosseum. It is an absolute monster of a building. But here's the crazy part. They decided to build it right on top of what used to be Emperor Nero's private lake. I mean, from an engineering perspective, that's a nightmare. You're putting a massive stone structure on soft, swampy ground. You'd think it would have just sunk straight into the mud. So, how did they pull it off with an absolutely brilliant piece of engineering? First, they dug out this massive 12-meter-deep trench shaped like a donut. Then they poured a single, massive, unbroken concrete foundation into it, and they mixed the concrete with heavy basalt rock to give it serious weight and stability, spreading the Colosseum's insane load perfectly. To top it all off, they built this complex drainage system 8 meters underneath everything just to keep the whole foundation dry. But what's really amazing is how they thought vertically. It wasn't just about the foundation. To get the Colosseum soaring 48 meters into the air, they zoned their materials. Down at the bottom, they used that heavy basalt concrete for a super solid base. But as they built higher and higher, they switched to concrete mixed with lighter stuff, like volcanic pumice for the upper vaults. This made the top of the building way lighter, which reduced the weight and the outward push on the lower levels. It was just this incredible marriage of logistics and smart structural design. And this shows you just what a huge leap they made. A traditional basilica, it was basically a forest of columns holding up a pretty simple timber roof. But then you look at the Basilica of Maxentius, they just threw that old design out the window. They used these gigantic concrete vaults to create this massive, wide-open space filled with light, with spans of over 25 meters. That was something that was totally impossible with the old ways of building. If you look at the vaults that are still standing, you can see these incredible octagonal coffers. Now, they look decorative, sure, but their main job was structural. They were designed to carve out tons of dead weight without losing strength, kind of like how a modern steel I-beam works. And because the whole thing was one solid piece of concrete, a monolithic core, it could handle earthquakes way better than stone masonry, which has thousands of weak little mortar joints that can just crumble apart. Okay, so they conquered scale, but their ambition didn't stop there, not even close. Next up, they used concrete to master the environment itself. We're talking controlling insane heat, managing huge amounts of water, and even reshaping the land. Just think about the challenge of the baths of Caracalla. The hot room, the caldarium, was kept at over 40 degrees Celsius, that's over 100 Fahrenheit, with 100% humidity, day in, day out. A normal building would just crack and fall apart under that kind of constant thermal stress. The Roman solution? A fully integrated system. The huge monolithic concrete dome could just expand and contract, soaking up all that thermal stress.
But the real genius was in the walls. They were built with these hollow tiles called tubuli. Hot air was piped through these tiles, and get this, the concrete for the walls was poured directly against them. The heating system wasn't just in the building, it was the building. And what about all that water? For things like pools and cisterns, they had a special waterproof concrete called opus signinum. They'd just crush up old pottery and tiles, mix it with lime, and create this unbelievably dense hydraulic seal. How good was it? Well, many Roman cisterns are still watertight today, 2,000 years later. It's just incredible. And this is where it gets just completely mind-blowing. At the Sanctuary of Fortuna, they didn't just build on the landscape, they completely rebuilt it. They used these colossal concrete substructures to turn a rugged, jagged mountainside into a series of 6 massive, perfectly ordered terraces. In their hands, concrete became like an artificial geological force. They were literally terraforming the planet to match their vision. So, for centuries, we thought we had a pretty good handle on how these structures worked. But modern science, modern analysis, is forcing us to rethink basically everything, and it's revealing a level of genius that's even deeper than we imagined. So let's take a look at Trajan's Market. Think of it as an ancient Roman shopping mall. It's an incredible building, but for decades, historians and engineers have been arguing about how its massive vaulted hall is actually still standing. So the old theory was that the arches on the side were acting like flying buttresses on a Gothic cathedral, pushing back against the main vault to hold it up. But it turns out modern computer analysis has totally flipped that idea on its head. The concrete vault is so strong and so rigid, it acts more like a solid lid. There's hardly any outward push at all. This shows they weren't just copying old ideas from stone construction, they were actually designing based on the real-world properties of concrete. And here's another great myth busted. You see these brick ribs inside the concrete? For years, everyone just assumed they were for reinforcement, like rebar is for us today. The reality is actually much, much cleverer. See, there was a timber crisis, and large wood beams were hard to get. So they built these thin brick lattices first. They acted as a guide frame and let them pour the vault in smaller chunks, which meant they needed way less of that expensive wooden scaffolding underneath. It was a brilliant workaround. So as we start to wrap this up, what does all of this really tell us? Well, it paints a whole new picture of Roman engineering genius. It's one that's less about a single secret recipe and more about a holistic, incredibly clever, problem-solving mindset. So let's just recap the core principles, their playbook, if you will. They practiced empirical design, figuring out how concrete actually behaved, not just how theory said it should. They mastered material zoning, putting the right stuff in the right place, heavy down low, light up high. They were pioneers in systems integration, making the heating system and the structure one and the same. And they were super pragmatic, using material substitution to cleverly solve resource shortages.
When we picture the Roman Empire, what comes to mind? Usually it's military might, right? Disciplined legions just marching across the known world. But what if the real secret to its power, the thing that let it last for so long, was something way more fundamental, something they were literally mixing up from dirt and rock?
Look, the Roman armies were absolutely formidable, no doubt about it. But they couldn't have projected all that power, secured all that trade, or held together that huge territory all on their own. They marched, and the empire thrived on an infrastructure that was built from a truly revolutionary material.
That's right, concrete. Today we're going to explore how Roman concrete wasn't just for building cool monuments. No, it was the essential connective tissue that really held the entire empire together, completely reshaping its roads, its economy, and its whole society.
Okay, let's dive right in. We'll start with the first and maybe the most visible effect of this incredible innovation, the amazing Roman road network.
So take a look at this. The real genius is hidden right there in the middle. This wasn't just about stacking stones. The Romans totally engineered this. They poured 2 different layers of concrete, the coarse rudis and the finer nucleus, to create one single, solid, waterproof slab.
And that simple idea was a total game changer. It meant their roads wouldn't just turn into a muddy swamp every time it rained. And that smooth, hard surface made it so much easier for wheeled carts to travel really long distances. So this wasn't just about making durable roads, it was an engineered solution to speed up the economic pulse of the entire empire.
And the scale we're talking about here is just immense. 400,000 kilometers. That is enough road to circle the entire Earth 10 times. It was an empire connected by these arteries of stone and concrete, and it was all thanks to this one foundational material.
So let's follow this ripple effect a little further, because this building boom didn't just change the landscape, it fundamentally reshaped the Roman workforce and really their whole society.
So think about it this way. Before concrete took over, if you wanted to build something impressive, like a temple, you needed a bunch of highly skilled stone cutters. And that was a pretty small, pretty expensive group of people. But concrete construction completely flipped the script. Suddenly, it wasn't about having intricate skills. It was about having sheer energy, the manpower to mine stuff, haul it, and mix it all together.
And this led to a process that we now call de-skilling. What that basically means is that a small team of skilled foremen could manage a massive army of unskilled laborers, or soldiers, or slaves, who were pretty much just pouring rubble and concrete. This let the Roman state scale up its construction projects at a speed and a size that nobody had ever seen before.
And here's the crucial point. Even though an individual unskilled worker might have earned less than, say, a master mason, the sheer volume of these huge concrete projects meant there was consistent employment for the masses. It basically acted as this huge stabilizing force for the Roman lower classes, almost like a massive state-sponsored jobs program.
Okay, but the impact didn't stop with the labor force, not even close. To actually make all this concrete construction possible, Rome had to build an entirely new industrial and logistical economy just to support it.
See, you couldn't just pour concrete into a giant, messy pile. You had to contain it somehow. The Roman solution was to use mass-produced bricks on the outside. So to build with concrete on this crazy, unprecedented scale, they first had to become masters at mass-producing the containers for it.
And we know for a fact this was a huge, centralized operation. How? Well, archaeologists have found brick stamps from factories in Italy's Tiber Valley all over the empire. We're talking from Gaul all the way to North Africa. These weren't little local shops. These were enormous factories, often owned by the imperial family itself, exporting their products all across the Mediterranean.
Just stop and think about what that implies for a second. The demand for concrete directly created this incredibly complex, state-driven supply chain. It pushed them to develop centralized factories, giant ocean-going transport ships, river barges for inland delivery, sophisticated quarry management, the whole shebang, connecting the entire empire in this web of industry and trade.
So when you start to connect all these dots, the roads, the labor, the economy, you begin to realize that for the Romans, concrete was so much more than just a simple building material.
It really was the foundational technology that made Rome's physical expansion, its deep economic integration, and its very unique social order all possible. It was the unseen blueprint that allowed the empire to be built in the first place, to function and to last for centuries.
So this is the big question, right? Did one of the greatest engineering civilizations in history just collectively forget how to make their most important building material? It just sounds too simple. Like a whole society just misplaced the index card with the formula on it. And this is the story we've all kind of picked up. The Roman Empire collapses, and poof, the knowledge just evaporates into the Dark Ages. It's a nice, tidy explanation. But the truth is, this wasn't a case of collective amnesia. It was a story of systemic collapse. And it all starts with something surprisingly mundane, a trip to the grocery store.
Yeah, that's right. The first huge piece of this puzzle isn't about lost blueprints or forgotten chance. It's about logistics. To really get it, you have to know about their so-called magic ingredient. Okay, so here's the secret sauce. Roman concrete wasn't just cement and rocks. What made it so incredible, what allowed it to harden even underwater, was this very specific volcanic ash, Pulvis putillanus. And here's the kicker. You couldn't get it just anywhere. You had to get it from one place, the Bay of Naples near modern-day Pozzuoli. For a long time, that wasn't a problem. When the empire was strong and the Mediterranean was basically a Roman lake, you could ship tons of this ash wherever you needed it for a big project. But then, well, you can see things started to fall apart. The Gothic Wars fractured the trade routes. Then Vandal pirates made shipping a nightmare. The whole economy shrinks, and suddenly, trying to ship a heavy, low-value good like volcanic ash hundreds of miles away becomes pretty much impossible.
And this quote just puts it perfectly. It's not that a builder in Spain or Britain suddenly forgot the mix. It's that he couldn't get the one ingredient that made it all work. The supply chain was toast. The grocery store, for all intents and purposes, was closed for business.
But a broken supply chain was only half the story, because even if you could get the ingredients, The actual process of making this stuff, well, it was incredibly dangerous, and that knowledge was fragile.
We're not talking about mixing up a bag of Socrate from Home Depot. The Romans used a technique called hot mixing, where they added quicklime directly to the mix. This sets off a violent exothermic chemical reaction. I mean, it gets incredibly hot. We're talking about a process that could give you horrific chemical burns, or literally blind you if it splashed in your eyes. This was a seriously dangerous craft.
And you can really see the massive trade-off they were facing here. On one hand, you've got the Roman hot mixing method. It takes a ton of skill, it's extremely dangerous, but you get that legendary self-healing concrete. On the other hand, you have the later technique of slaking the lime first, basically adding water to it beforehand. It's safe, it's easy, anybody can do it. The problem? The concrete you get is just standard. It's a huge step down in quality. But hey, when the alternative is getting blinded, you can see why people started choosing the safer, easier option. And this is so crucial. You don't learn how to handle something that can melt your skin by reading a scroll. You learn it by being an apprentice to a master, day in and day out on massive state-funded construction projects. So what happens when those giant aqueducts and amphitheaters stop getting built? That master-to-apprentice chain just breaks. The hands-on, nuanced knowledge that kept people safe, it just fades away.
All right, so we've got supply chains gone and we've got a dangerous craft that's been lost. But there's one more piece to this story, and it's a big one. It's about a flaw in our own thinking. It's a concept called survivorship bias. Basically, it's a mental trap where we make judgments based only on the things that survived, and we completely forget about all the things that failed and disappeared. And when it comes to Roman concrete, this bias changes everything. Think about it. We are amazed by the Pantheon, the Colosseum, the aqueducts. These were the moonshot projects of their day. They were massively over-engineered with the best materials, the best craftsmen, and unlimited state funding. But they were not the average Roman building. Not even close. Your average Roman apartment building or warehouse was built to a much, much lower standard. And that's the bias in action. We see the magnificent exceptions that were built so well they could last for 2 millennia. What we don't see are the thousands upon thousands of structures that failed, that crumbled away centuries ago from shoddy work, bad materials, or just a lack of upkeep. Our whole perception of Roman concrete is skewed because we're only looking at the champions. So when you put all these pieces together, the logistics, the crafts, and our own bias, you start to get a much clearer and much more accurate picture of what really happened. So, see, the recipe wasn't lost like you'd lose your car keys. The entire civilization that supported it was lost. The complex trade network needed for that magic ingredient, it vanished. The constant, large-scale practice needed to keep a dangerous craft alive, that disappeared too. And on top of all that, our modern view is warped because we only see the miraculous survivors. It wasn't one thing, it was everything all failing at once.
Today, we are diving into one of the most incredible and honestly underrated engineering feats of the ancient world. This is the story of how a single technological breakthrough let an empire completely defy geography and literally build its dominion on water.
So let's get right into it. The Roman Empire was, at its very core, a thalassocracy. Now that's just a fancy word meaning its power came directly from the sea. Its entire survival hinged on controlling the Mediterranean, which they proudly called Mare Nostrum, our sea. This was the superhighway for their legions, their trade, and crucially, their food.
But here's the catch. What do you do when the very coastlines you need to control are totally unsuitable for the empire you're trying to run? What happens when the sea, your greatest asset, suddenly becomes your biggest obstacle?
So what was this massive roadblock? Well, this gets us to the fundamental challenge Rome faced, its strategic Achilles heel, the problem of the coastline itself.
And you can see the huge mismatch right here. On one side, you have the empire's needs. Rome had to have deep water ports for its colossal grain freighters and totally secure supply lines for its legions. But on the other side, the reality? In critical places like Italy and the Middle East, you had straight sandy shores with absolutely no natural sheltered harbors. This was a logistical nightmare that seriously threatened the entire imperial project.
So how in the world did they solve a problem that seemed, well, unsolvable? They invented a secret weapon, a truly revolutionary material that would, quite literally, become the foundation of their maritime power.
And that weapon was hydraulic concrete. Now, this was not your everyday concrete. By mixing volcanic ash, which they called pozzolana, with lime and water, Roman engineers created a material with an almost magical property. It could set and actually harden underwater. This was the absolute game changer.
Okay, so having this miracle material is one thing, but how did they actually use it to build something in the middle of the open sea? Well, they developed this brilliant method called the caisson technique. First, they'd build a massive double-walled wooden box, kind of like a barge, on shore. Then they'd float this huge empty box out to sea, right where they needed to build. Next, they'd start filling it with the hydraulic concrete mix, and the incredible weight would sink the whole thing perfectly into place on the seabed. And then the magic happens. The concrete sets, creating a single, solid, man-made rock, the perfect foundation for a pier or a breakwater.
With this incredible technology, Rome could now do more than just sail the coasts. They could conquer them. Let's take a look at our first case study, Caesarea, to see how this became a powerful tool for military control.
So we're looking at Caesarea Maritima, built on the coast of Judea by a client king of Rome, Herod the Great. Now, this coastline was infamous for having no natural harbors at all. The goal here was really twofold. First, to plug Judea into the Roman economy, but even more important, to give the Roman legions a reliable, deep-water port for military operations in the very volatile East.
The scale of this project was just staggering.
To make it happen, they needed 24,000 cubic meters of that key ingredient, the volcanic ash. And get this, that ash had to be shipped over 2,000 kilometers all the way from the Bay of Naples to Judea. This just shows you the insane trans-Mediterranean supply chain Rome could command for a project it deemed strategic.
And the result of all this? Caesarea became the provincial capital and the main base for the legions. Let's be clear, without this concrete harbor, the Roman campaigns during the Jewish-Roman Wars, including those legendary sieges of Jerusalem and Masada, would have been logistically a nightmare, if not completely impossible.
So we've seen how concrete ports helped conquer the provinces, but an even bigger one was needed for something even more fundamental, the very survival of the empire's heart, the city of Rome itself.
And here's why. The city of Rome had over 1 million people. To keep them fed, it had to import more than 400,000 tons of grain every single year. The city's old river port at Ostia just couldn't handle that kind of volume. It was a ticking clock.
So the emperors Claudius and then Trajan kicked off the construction of Portus, a massive artificial harbor complex built almost entirely out of concrete, and it solved every single one of Ostia's problems. It was deep enough for the biggest ships, it was protected from storms, and its huge concrete docks and warehouses could handle the relentless flow of grain needed to keep Rome alive.
But Portus wasn't just Rome's pantry. It was also called the lung of the imperial army. You see, that grand supply didn't just feed the population, it fed the military. It guaranteed political stability and the emperor's ability to wage war. Portus was a critical military asset, plain and simple.
So you see, these weren't just one-off showcase projects. This technology was scaled up, creating a network that became a foundational piece of the entire empire, a true legacy, cast in stone.
You can trace a line from Caesarea in the east to Portus at the very center of the empire, and all the way to the stormy, tidal waters of the English Channel and places like Dubras, what we call Dover today. Up there, concrete harbors were absolutely essential for supplying the legions fighting on the frontier in Britain.
So what does this all mean? Ultimately, hydraulic concrete gave Rome the power to reshape coastlines to fit its imperial needs. It was the key technology that allowed them to build permanent, all-weather infrastructure pretty much anywhere they wanted, knitting together the most distant and difficult parts of their empire into one functioning system.
Okay, so let me ask you this. Just picture it. You're a Roman general. You've marched your army for weeks, you're right on the edge of enemy territory, and this is what's staring you down. A massive, fast-flowing river, a full kilometer wide. You have to get tens of thousands of soldiers, all your cavalry, and your heavy siege engines to the other side. So how do you do it? I mean, how is that even possible?
Well, for just about every other army in the ancient world, the answer was, you don't. A river that big was an impossible barrier, a natural fortress. The campaign would just stop right there. But for the Romans, it was just another challenge, a problem that needed an engineering solution.
To really get what the Romans pulled off, you first have to appreciate the scale of the problem. Let's talk about the incredible power of these natural barriers.
I mean, think about it. You can besiege a wall, you can break it down. But a river like the Danube or the Rhine, that's a completely different kind of obstacle.
It's relentless, it's always moving, and it can stall an invasion for months, completely wrecking your supply lines. It was, without a doubt, nature's ultimate defensive line.
So how did Rome turn these absolute campaign killers into little more than speed bumps? Well, they had a secret weapon, a truly revolutionary technology that changed absolutely everything.
The key words here are harden underwater. This was not your average concrete. The Romans figured out that by mixing volcanic ash into their mortar, they created a material they could literally pour into a flowing river, and it would set into solid rock. This stuff was the absolute game changer for all of their massive water projects.
But look, being a genius inventor is one thing. Being a genius logistician is another. The best volcanic ash they had, this stuff called pulvis putillanus, came from Italy. Trying to ship tons of that all the way to the German frontier would have been insanely expensive. So what did they do? They adapted. Roman military engineers on the ground actually found a local volcanic rock called trass that worked just as well. This is so crucial. It shows they weren't just following a recipe, they were localizing their material science, making their best tech affordable and practical across the entire empire.
All right, so let's see how this all came together and what might be one of the most spectacular engineering feats of the entire ancient world.
Just take that number in for a second. 1,135 meters. That's over a kilometer long. This wasn't some temporary wooden bridge. We're talking about a permanent, heavy-duty structure built across the Danube, one of Europe's mightiest rivers, for the sole purpose of launching an invasion. The sheer audacity is just staggering.
And get this, they did it in just 2 years. Under the direction of the brilliant architect Apollodorus of Damascus, Roman legions built this marvel. Why? Because Emperor Trajan needed a permanent supply line for his war against the Dacians. So, they simply decided to build one. So how on earth did they build 20 massive piers right in the middle of a rushing river? It was a masterpiece of technique. They most likely used something called cofferdams. Essentially, you build a watertight box in the river, then you pump all the water out of it. Suddenly, you have a dry workspace right on the riverbed where you can pour your incredible hydraulic concrete foundations. Simple in concept, but unbelievably difficult to actually pull off.
And this created a total strategic transformation. Before the bridge, the Danube River was Dacia's greatest protector, its natural shield. After the bridge, that exact same river became Rome's year-round highway for troops and supplies, leading deep into enemy lands. They literally turned their enemy's best defense into their own greatest asset.
So what was the payoff from this one bridge? Well, it was massive. It led directly to the total conquest of Dacia and the capture of its incredibly rich gold mines. That gold was so plentiful, it actually paid for two of the most iconic buildings in Rome, Trajan's Forum and the Pantheon, all while eliminating a dangerous threat from their border. All of that from one single engineering project.
But building bridges over rivers was just one tool in their kit. The Romans also reshaped the landscape itself by digging massive canals for military purposes.
You can see a couple of great examples right here. Way back in 12 BC, the Fossa Drusiana linked the Rhine to the North Sea. This allowed the Roman fleet to move into Germany without having to brave the treacherous open ocean. Then, decades later, Corbelo's Canal connected the Rhine and the Meuse rivers, creating a safe internal waterway to protect supply ships from nasty North Sea storms.
And there were so many reasons to do this. It was about safety and logistics for sure, but it was also about speed. You could redeploy fleets much faster. These canals acted as secure communication lines right behind the frontier. And there was even a bonus. They kept the legions busy, disciplined, and productive when there wasn't any fighting going on. It was just a brilliant, multi-purpose strategic investment.
So let's bring all of this home. What does this complete mastery over water really tell us about the true source of Roman power?
I think this quote really says it all. The Roman mindset was just fundamentally different. For them, a river wasn't an obstacle, it was an opportunity. It was a barrier that you could convert into a highway. They didn't just fight on the map they were given, they redrew the map to suit their own needs.
So the ultimate takeaway is this. Of course, the Roman legions were formidable, but their dominance was secured by the engineers. It was their ability to build, to pour concrete, to dig canals, and to fundamentally reshape the physical world that made their military machine nearly unstoppable.
For centuries, Rome was all about one thing: growth. Its legions were constantly on the move, always pushing the borders outward. But, that can't last forever. Eventually, the empire had to make a massive pivot. They shifted from being an empire of conquest to an empire of fortification. The whole mission changed. It was no longer about grabbing new territory, it was about holding on tight to what they already had. And this huge strategic change really gets going under emperors like Hadrian. Rome had basically reached its practical limits, so the new game plan was all about consolidation, about locking down the borders. But securing the massive territories they'd already won, well, that turned out to be a whole new kind of problem.
And it was a massive problem. I mean, just try to imagine it. Your job is to secure a frontier that stretches from Britain all the way across Europe and deep into North Africa. You can't have legions posted everywhere at once. It's just impossible. You need something else, a permanent physical statement of your power that says, this is Rome, and you don't cross this line.
So what was their solution? It was as ambitious as it sounds. They decided to literally build the border. This wasn't just going to be a line on a map. Oh no. The plan was to construct a massive fortified frontier that would physically separate the Roman world from everybody else.
This enormous project was called the Limes. And you've got to understand, it wasn't just one big wall. It was way more complex than that. Think of it more like a complete defensive system. A whole network of walls, sure, but also ditches, forts, and watchtowers, all working together to control movement and project Roman authority.
The scale here is just staggering. We're talking about roughly 5,000 kilometers of fortified border. To build and maintain something that enormous required a completely revolutionary approach. You needed a standardized, scalable method that you could use anywhere in the empire, from a misty forest in Germany to a desert in Syria.
And this is where the genius of Roman engineering really shines. Their method was simple but incredibly effective. Instead of needing highly skilled stonemasons for every single wall, soldiers could just build 2 stone faces and then pour a core of mortar and rubble right in between. The real secret sauce was the mortar. They often used volcanic ash, what they called pozzolana, and it created this unbelievably strong binder. It was even water resistant. This was a game changer. It allowed for standardized fort designs that could be built fast and cheap anywhere. This wasn't about artistry. This was about military construction on an industrial scale.
So, all this grand strategy is great, but what did it actually mean for the people on the ground? For the soldiers living on the frontier? Well, to find out, let's zoom way in to a single fort called Vindolanda, just south of Hadrian's Wall in Britain. This shift to building with stone and concrete fundamentally changed what it meant to be a Roman soldier. They went from being a mobile expeditionary force, living out of tents or temporary wooden barracks on the way to the next fight, to being a permanent garrison. They were putting down roots, anchoring Roman power right into the landscape for centuries.
This quote just nails it, doesn't it? Building the commanders' houses and the main headquarters with concrete foundations was a huge statement. It said, loud and clear, we are here and we are not leaving. This wasn't some temporary camp anymore. This was a small, permanent piece of Rome right on the edge of the world.
Now, this shift to permanent concrete buildings had an incredible and totally unintended consequence. When the Romans built a new stone fort, they'd just knock down the old timber one and seal that layer of rubble and debris with clay and concrete. What that did was create an oxygen-free environment. And in that environment, fragile things that would normally rot away, like leather shoes and even handwritten letters on wood tablets, were perfectly preserved. It's an accidental time capsule sealed shut by the very material that defined their permanence.
So if we dive even deeper into the fort, we find what was arguably the army's most critical weapon. And it's the one building that depended most on concrete technology. We're talking about the structure that kept all the soldiers fed. You know the saying, an army marches on its stomach? Well, for a permanent garrison stuck on a remote frontier, a secure food supply wasn't just important, it was absolutely everything. And that is why the Horium, or the granary, was the most heavily engineered and robust building in the entire fort, period. And these granaries were just marvels of practical engineering. The floors were raised up on all these little concrete pillars to let air circulate underneath, which was crucial for keeping the grain dry. The walls were incredibly thick and buttressed, strong enough to hold back the immense pressure from tons and tons of grain. These were basically concrete super silos, designed to withstand a long siege, supply chain problems, anything. They guaranteed survival.
All right, let's zoom back out. From a single granary all the way up to the entire 5,000-kilometer border, a very clear picture starts to emerge. a humble building material, was right at the very heart of Rome's grand strategy for survival. So here's the ultimate takeaway. Roman concrete was so much more than just a mix of lime, rock, and water. It was an instrument of imperial policy. It's the technology that allowed Rome to shift its entire strategy. It made the permanent frontier possible, it transformed the army into a garrison force, and it secured the food supply that held the whole thing together. It was, quite literally, the foundation of the empire's long survival. Offensive siegecraft. Now, this is way more than just, knocking down a wall. This was a whole philosophy. It was about using these massive, mind-boggling engineering projects to rig the game, to take luck completely out of the equation, to make victory inevitable. And if you want the perfect, most insane example of this in action, we have to talk about the Siege of Masada. Seriously, this wasn't just a battle. It was basically a terraforming project with the simple goal of crushing a rebellion. So picture this. It's 73 AD. A whole Roman legion shows up at Masada. And Masada is basically an impossible target. It's this huge fortress sitting way up on a sheer cliff in the middle of nowhere. So what do? Well, if you're the Romans, the solution is simple. You don't go through the mountain. You just build a highway right up to the front door. But that raises a huge question, right? How on earth do you get your heavy gear, we're talking giant siege towers, massive battering rams, up a cliff face? Well, their mission was to build a ramp strong enough to carry the entire weight of their war machine right to the enemy's walls. And just look at the genius of how they did it. They start with this huge base of earth and wood. They build retaining walls to keep it all stable. But here, this is the real magic. They used mortar to consolidate the whole surface. They literally paved a highway into the sky, making it solid and stable even in the middle of the shifting desert. The scale of this thing is, well, it's just hard to wrap your head around. That ramp rose 113 meters. To put that in perspective, that's like building a ramp all the way to the top of a 37-story skyscraper. It's just a staggering monument to what military engineering can do. Okay, so they could do massive brute force projects. But that's not the whole story. Roman engineering was also about incredible precision, and that really shines through when you look at their artillery. I mean, think about it for a second. You've got this giant crossbow, a ballista, that hurls huge stones. Every time it fires, there's this massive, violent kickback. So how do you keep it aimed? How do you hit anything twice? Right? If you just stick one of these things on the dirt, it's a disaster. The recoil knocks it out of position every single time. Your aim is shot, you're constantly having to re-aim, and your rate of fire just plummets. But what if you build a special platform, one that's perfectly level and hardened with concrete? Suddenly, you've got a rock-solid base. Now you can fire accurately, quickly, and just keep pounding the enemy. And, of course, the Romans had a name for these. Balisteria. And we're not just talking about a flat piece of ground they cleared off. No. These were custom-built, engineered platforms specifically designed to make their artillery deadly accurate. And the firepower they could unleash from these things was just incredible. Take the Siege of Jerusalem. We have records of ballista launching 26-kilogram stones. That's nearly 60 pounds. And they were launching them over 370 meters. From those steady concrete platforms, they could just sit back and systematically tear down a fortress wall, piece by piece, from way outside of arrow range. And the best part is, this isn't just a theory. We know this for a fact because of the archaeology. At places like Gamla and Jerusalem, archaeologists have found these dense clusters of ballista stones. It's like a footprint, showing us exactly where these engineered firing positions were. The evidence, you could say, is literally written in stone. So, let's pull all this together. When you look at the evidence, the whole picture of how the Romans waged war, it really starts to shift. You know, the classic image of Roman conquest is the legions, right? All those guys marching in perfect rows, a sea of shields and swords. But maybe, just maybe, their biggest weapon wasn't the sword. It was the shovel. It was their almost unbelievable ability to reshape the battlefield itself to their advantage. They didn't just fight on the terrain they were given, they built the terrain they wanted. They turned impossible fights into simple matters of logistics. So really, we have to rethink how we see Roman power. It wasn't just about tactics or logistics or politics. There's a fourth pillar holding it all up, And it's just as important. Offensive engineering. This wasn't some sideline activity. It was absolutely central to how they conquered the world.
So let me ask you this. What was Rome's #1 tool for building and, more importantly, holding its massive empire? Was it the disciplined legionary, the famous gladius sword, or was it something way less glamorous, but a whole lot more permanent? And here's the kicker. The sword, sure, it conquered territory, no doubt about it, but it was concrete that actually integrated the empire. See, conquest, that was just the first brutal step. The real Roman genius was turning enemies into citizens. And for that, you need a totally different kind of tool.
Which brings us to our first big idea: seduction by engineering. Seriously, Rome knew that you couldn't rule by force forever. You had to convince people that being Roman was just, well, better.
And this is a textbook case of what we now call soft power. Instead of just ruling with an iron fist, Rome dangled these amazing cultural attractions and amenities in front of people. They made Roman life look so good that local bigwigs were practically lining up to get in on it.
And the ultimate symbol of this whole strategy? The Roman bathhouse. Now, this was not just a place to wash up. Come on, it was the social hub of the town, a miracle of public health and, let's be honest, a massive flex of Rome's technological muscle. These things were basically engines of Romanization, plopped down in provincial towns to sell the Roman dream.
So how'd they build these incredible places? You guessed it, concrete. Those huge, wide-open, hot and cold rooms, the caldarium and frigidarium, they were only possible because of what concrete could do. It let them build massive vaulted ceilings and domes without needing a whole forest of columns getting in the way. It created space and a sense of awe.
And get this, they even figured out central heating with something called the hypocaust system. They used concrete to create these heat-resistant subfloors, so you'd have hot air from a furnace circulating underneath, radiating warmth up into the room. I mean, they were literally building comfort and luxury right into the foundations.
Okay, just picture it. You're living on the frontier in Britain or Germany. It's cold, it's damp, and all of a sudden, these invaders show up and build a public spa with heated floors and pools of steaming water. A bathhouse wasn't just a building. It was a powerful argument for Roman rule. It was a promise of a better, more comfortable life.
But seduction was only half the story. Rome had another play in its book, and it was the total opposite, pure intimidation. They used concrete to create an architecture of awe, and the message was crystal clear. We are here and we are never leaving.
Just look at this number, 43 meters. That's about 141 feet. That is the diameter of the Pantheon's dome in Rome. It was built almost 2,000 years ago, and it is still the largest unreinforced concrete dome on the entire planet. Think about that. This wasn't just architecture. It was a statement of almost godlike power. And the Pantheon wasn't some one-off vanity project. Oh no, this same feeling of immense, unstoppable permanence was stamped all across the empire. You'd see it in the massive concrete walls of a fortress, the sky-high arches of an aqueduct, the solid, imposing feel of a basilica.
And the psychological impact of this, I mean, it must have been staggering. Imagine you're from a tribe that lives in wooden huts, and then, right on your border, the Romans throw up a concrete fortress that looks like it grew out of the mountain itself. The difference in power and permanence, it's just overwhelming.
You wouldn't just be impressed. You'd probably see it as the work of actual giants. I mean, how else could you explain it? It would look like something built by a force so far beyond your own that fighting back would seem, well, completely insane.
And make no mistake, this architectural intimidation was a deliberate, calculated tactic. Every single one of those massive, concrete structures was a piece of propaganda, reinforcing the idea that Rome was eternal and resisting them was totally futile.
So, okay, this concrete had huge effects back then. But what's truly mind-blowing is the long-term legacy. These structures didn't just define the Roman world. In some cases, they're still shaping our world today.
And the perfect case study for this is the Limes Germanicus. That's Rome's huge fortified border that ran through modern-day Germany. Recent studies, and this is wild, have found that the impact of this ancient concrete line didn't just vanish when Rome fell. It kept shaping the region for centuries to come.
The research here is just fascinating. The exact line of that old Roman wall, it lines up with cultural and economic divides that are still there today. It probably has to do with the infrastructure and settlement patterns that got locked in 2,000 years ago.
It's even been shown to influence things like regional personality traits and modern development. I mean, the ghost of that concrete wall is literally still with us.
So you see, that concrete border was so much more than a wall. It became a civilizational dividing line, splitting the Romanized world from the non-Romanized world in a way that would echo for 1,000 years. So this discovery is doing way more than just rewriting history books. It's making us look at this ancient solution to solve two of our biggest modern crises, our crumbling infrastructure and the enormous carbon footprint for making cement. And when you put them side by side, the difference is just staggering. Modern cement production is responsible for something like 8% of the world's CO2 emissions, and it gives us a product that's brittle and doesn't last. This Roman-inspired approach, on the other hand, uses less energy and creates a material that actively repairs itself to last for centuries, not just a few decades.
This is exactly why it's no longer just an academic thing. We desperately need more sustainable building materials, and that need has turned this ancient tech into one of the hottest fields in modern engineering.
And this has kicked off a whole new wave of innovation. You've got companies taking these old-school principles and souping them up with modern science. An MIT spin-off called Sublime Systems found a way to make lime without a high-heat kiln. Other companies, like Basilisk, are making biomimetic versions that use special bacteria to get that same self-healing effect. It's incredible stuff.
And the potential here is just enormous. Just take one of the Roman tricks, swapping out some of our modern cement for volcanic ash. That one change could cut the energy footprint of concrete by 16%. Now, when you're talking about the most used material on the planet, 16% is a monumental, game-changing number.
So you see, this isn't just about making better concrete. It's about bringing back a totally different philosophy of building, a philosophy built around permanence and resilience. One researcher put it perfectly. For so long, we've built a disposable world. The goal now is to, and I quote, restore the concept of eternity to the vocabulary of construction. I mean, how powerful is that? So where are we going to see this new old technology first? Well, it might not be in your local skyscraper just yet. It's perfect for the massive, foundational projects our civilization relies on. We're talking about self-healing seawalls that get stronger over time, harbors that can stand for centuries, and foundations for bridges and buildings that are designed to last for the next 1,000 years. And that really leaves you with this one last thought. We have just unlocked a 2,000-year-old secret that could genuinely revolutionize our future. So if the key to sustainable building was just sitting there, hiding in plain sight in the ruins of Rome, it makes you wonder, what other ancient secrets are out there, just waiting for us to rediscover them?